All right, hello grade 12s. Today we are looking at solving logarithmic equations. Okay, let's get started. If we have just a single logarithm, our strategy is to convert our logarithm into an exponential / power statement instead. Remember, if we have a to the b is equal to c, the equivalent logarithmic statement would be the log base a of c is equal to b. Okay. So let's give it a shot. Okay, so if you have log base 2 of x is equal to -3, what is the equivalent way of saying that with exponentials? Well, that's going to be the 2 to the exponent of -3 is equal to x. And beautiful. Okay, we have already x isolated, so let's evaluate. That's 1 over 2 to the exponent of 3, which is the same thing as saying 1 over 8. Wonderful. Once again, it was with a single log. Our strategy is to rewrite as an exponential. And remember, another way to think about log is the following question. To what exponent do you have to raise this x to equal this? Well, if the answer is -2, then the answer is, okay, x to the -2 is equal to 1 over 64. Okay, let's give this a shot now. We have a -2 as the exponent. Why don't we take the reciprocal of both sides? Okay, here is a cool fancy trick. You can apply an operation of the exponent of -1 on both sides. Let's give it a shot. This becomes x squared is equal to, well, the reciprocal of this is simply 64. And then the square root is equal to plus or minus 64. X is equal to plus or minus 8. However, take a look. This x is representing the base of a logarithm. Because the government has decided so, they have told us in grade 12 advanced functions, the base value will always be greater than 0 and not equal to 1. So for our purposes, we're strictly going to consider only x equals +8. However, you could have a -8 as your log. We're going to get into some weird territory here, but not a grade 12. Okay, we'll leave it there. Equations when we have exactly 2 logarithms with the same base. If we have 2 logarithms, well, we'll put one on each side, and we'll use the same strategy we use with exponentials. If you had like 3 to the x plus 7 is equal to 243 to the x plus 1, our strategy was to make both of them agree on a base. Well, 243 is the same as 3 to the exponent of 5, so 5x plus 5. And then we can say, oh yeah, the x plus 7 is equal to 5x plus 5. And then we can isolate 4x in this way, once we said, hey, if both of them have a base of 3, then, well, to be an equation, the exponents have to match because the exponentials are 1 to 1. That's basically it. Okay, so we're going to apply the same strategy here. If we can get their logs to agree and match, well, their inner parts, their arguments, must also match. Okay, let's give it a shot. Well, we're starting off nice and easy because, well, the logs are already agreeing. Therefore, the inner part of the log, the argument, 3x minus 2 is equal to 16. Okay, and now we're going to isolate for x. 3x is equal to 18, not -18. And then x is equal to 6. Beautiful. Okay, what if you have more than 2 logs involved? Well, we're going to use our different log laws to convert it so that we only are dealing with 1 log on each side. Reminder, if we have a sum of logs, that's the same as the product of their arguments. If we have a difference of logs, that's equal to a quotient of their arguments. And lastly, whenever we see a coefficient in front of a log, we can re-express that as an exponent. And by the way, these rules go vice versa. Sometimes it's handy to have one version, sometimes it's handy to have the other. Okay, let's have a look here. So for our purposes, we want to get to the point like we had before, where we have the log of one thing on one side is equal to the log of the another thing on the other side, and then we can say, okay, the thing inside the log is equal to the thing inside the other log. Okay, but we have to get to the point where we only have 1 log on each side. Let's make that happen. Okay, so how do we combine 2 logs that we're subtracting? Well, we're going to apply, log rule number 2. The difference of logs is equal to the same thing as the quotient. So the positive one goes on top, 30x, and the negative one goes on the bottom, 5, is equal to log base 2 of 12. Oops. And at this point, since we already have a single log on both sides, we can drop them. And we can also reduce this at the same time. So see you later, logs. And 30x divided by 5 is 6x is equal to 12. Therefore, x is equal to 2. On the right here, okay, so we have log x and 2 log x. Since these two parts are like the same term, it's like terms. So we have a 1 log x plus 2 log x. That's equal to 3 log x. Now be careful. Be careful. If I had something like log x plus log 2x, these things can't add because the things inside the logs are not the same, therefore not like terms. Maybe a safer strategy, if you're not comfortable with this, is to first re-express this thing out there. So let's keep it, oops. So let me show you the other way of doing this question. You would re-express the second log. So that would be plus log base x of 2, x squared. And then you would write this as log of x to the exponent of 3. Turns out it's going to be the same thing. Okay, let's have a look. So this is equal to 12. And we can write this as x cubed. So the s, the other the same, is equal to 12. And now we only have a single log on both sides. Cool. At this point, we are going to remind ourselves, hey, what is this log x without a base value? Well, if it's a common log without a number attached, is an invisible 10. So we're saying 10 to the exponent of 12 is equal to x cubed. Okay, then we're going to cube root both sides. Maybe another way you want to think about cube root is applying a 1/3 power on both sides. And then we get x is equal to 10 to the 4. Final answer. Okay, man, are these questions even real? All right, here we go. We have the same log on both sides. However, we cannot equate them until we deal with these coefficients. So these coefficients have got to go. We have to express them in a different way. Well, hopefully you remember there's a rule for that. Okay, well, if there's ever a coefficient in front of a log, we can re-express that as the exponent on the argument inside the log. So this too can travel and make its way into the exponent inside the log. Okay, and now we can apply the thing we have here. Okay, well, a single log on both sides. It's not cancellation, but we're making a conclusion. Since we're doing the same thing on both sides, same operation, then the thing we're operating on must also be equal. So we get the idea that x is equal to 5 squared, x is equal to 25. And once again, I want to reiterate, we have to make sure that there's no other operation going on except for the log. So if there's any coefficients, multiplying, adding, subtracting, whatever, anything like that has got to go or be re-expressed. Okay, we have the log base 6 minus log base 6 of x minus 1. Let's rewrite that. So then that's log of 6, subtraction means division inside the log, is equal to 1. And actually, I'm going to handle this one in a slightly unique way. And I want you to be flexible with what you're thinking here. Instead of immediately converting this to an exponential statement, which you could, you can make this x over x minus 1 is equal to 6 to the exponent of 1. I want you to think about, hey, could we convert a 1 into a log? What value would occupy here so that it would revert and come back to a 1? Hopefully you found the answer to be 6. And now we can apply the idea we're going for here. Log 6, therefore, this argument is equal to this argument. X over x minus 1 is equal to 6. Okay, all right. And at this point, we want to keep track of restrictions here. X cannot equal 1. Well, we don't even have to do that. We can just say x is greater than 0, x is greater than 1. In fact, this one takes precedence over here. Now, what are we going to do from this part here? We're going to multiply both sides by this x minus 1 here, multiplied by x minus 1. We can cancel out these denominators, and we get x is equal to 6 times x minus 1. Obviously, let's open up the brackets. 6x minus 6. Isolate for x. Let's bring the 6 over. So then we get 5x is equal to negative 6. X is equal to negative 6 over 5 as our final answer. Okay, and one more to go. We have the log base 5 of log base 3 of x. Well, we're just going to deal it one step at a time. First, this log base 5. Okay. We don't know what the answer to this is yet. However, we know the log base 5 of something is equal to 0. Therefore, well, what's the equivalent way of thinking about this? What exponent can be applied to the 5 to make it equal to a 0? Sorry. 5 to the 0 is equal to something. Okay. You know what? I'm going to reset this question. Sorry. I've redecided the way to explain this. I think maybe a cleaner way to go about this, if you don't see it yet, is to, if you're maybe a little intimidated by the double logs, make a change of variable. So we'll say let the letter, what's a good letter? H. No, H sucks. Let's go for t. T is equal to log base 3 of x. Okay, so we're going to convert this to a log base 5 of t is equal to 0. And remember the story of logs. The story of logs says, okay, to what exponent do I have to raise the 5 to equal the thing inside the log? Well, I already had the answer. The answer is 0. So 5 to the 0 is equal to t. Therefore, t is equal to 1. And, well, since we didn't actually start off with the t's, we have to put back the original definition of our log. Log base 3 of x is equal to 1. And one more time here. 3 to the exponent of 1 is equal to the insides of our log, x. Therefore, x is equal to 3. And let's do a little bit of backtracking. Let's actually do a check step. We have log base 5 of log base 3 of x. Okay, let's give this a shot. Log base 5 of log base 3 of 3. Okay, the log of something that is the same as the base is 1. Because you have to raise that thing to the 1 to equal itself. So we get a 1. And then, how do you produce a 1 using a base value of 5? What exponent makes that happen? The answer is 0. And beautiful. We get the 0 back that we're looking for. Let's just call this check. And beautiful. Hopefully you have a wonderful day. I will see you tomorrow.